boards. You will not be able to see the boards, but if you've got your notes, you can follow along. So that'll work. So at least you have the sound, you can go along with that. Okay. And it just is this side. It doesn't show the students. All right. Okay. So let's go ahead and jump into where we're at. I do have some PowerPoints that are on here, and you can find those here if you need some other resources to kind of go back through and explain the textbook a bit better. Because sometimes people just do not like reading a textbook. Y'all enjoy it? I don't really either. It's not like it's super fun for me. So this does have a breakdown of a lot of the concepts that you would need: molecular shape, molecular geometry, bond angles. It's got images to go along with it. I tend to not teach so much from PowerPoints because y'all can read. You don't really need me to read slides to you. So if you're finding that you don't necessarily want to read the textbook, the slides are a good way to take it in little bites, right? Kind of get little snippets. All right, so let's see where we're at with our objectives. We talked about Lewis structures last time and how to draw those out with bonds. All right, now I want to talk about periodic trends, electronegativity, and some resonance stabilized structures. So we're going to hit some of that today. Things that we've talked about a lot of this in this first objective with Lewis structures, the octet rule, electronic structure of the atom, electrons are on the outside in the quantum mechanical model. We've talked about covalent versus ionic bonding. And we're getting into the different ways that we can draw a particular compound with the resonance stabilized structures. We're going to jump into that a bit more. But first things first, periodic trends. Now I'm so excited about this marker. It's refillable. Let's put in a new one. So, look at that. That's awesome. And it's nice and dark, right? Periodic trends. Okay, so we've got electronegativity, electron affinity, ionization energy, atomic radius, now, let's see, metallic character. Okay. So periodic trends essentially are patterns on the periodic table. That's all they are, patterns on the periodic table. And the website that I like to use to show this is ptable.com. It sounds rude, but it's not. Periodic table, so it's ptable.com. We're going to pull this up. Not potable. Although that is a word. Really, I don't want that. I don't want the latest news. When you're really all freaking. Come on, there we go. I love this resource because you can go through and it has all of the periodic trends right here on the side. Okay? So, when we're dealing with periodic trends, one thing that I like to do to remind myself which direction everything goes. I draw out like something that looks like a periodic table. Of course, it's not perfect, but it gives me a general idea of what, I'm looking for. So when I move from left to right, wherever the direction's going, it means it's increasing. Electron affinity and electronegativity and ionization energy. So I've turned these into abbreviations. EN, EA, IE, I also have AR, metallic character. All right, so as I move up and across, electron affinity, electronegativity, and ionization energy increases. So, what do these words mean? What do you guys think these words mean? What's an affinity for something? I have an affinity for coffee. Yeah. What's an affinity for something? Come on. Work with me. I'm going to pull out my cards and call on people. What's an affinity for something? You have an affinity for something. I have an affinity for coffee. I have an affinity for superheroes. I have an affinity for sci-fi.
Something I like to do.
Something that I like, right? So electron affinity means likes electrons. I'm going to use E- for my electron. Electronegativity, because something likes electrons, it becomes more negative. So it becomes more negative. So if something likes electrons and it's collecting electrons, since electrons are negatively charged, it's going to become more negative, right? Ionization energy, what do you think that means? Well, if you're ionizing something, this part right here means a process, right? So it's the process of making what? What's that first word? Ions, there you go, y'all got this. Y'all got this. So the process of making ions. So this is the energy required. I'm going to take it a step further. Energy required to take electrons. The energy required to take electrons. What's a radius? Where do we see radius? In like everyday life. You're getting the radius of something. What shape does that have to do with? Circle, right? We often think about atoms as circles. I mean, it just helps with the math, right? The condoms do behave a little bit in that shape overall with where the electrons are. So atomic radius has to do with the size of the atom. Size of the atom. Metallic character could be like, person that goes to a concert compared to metal. But in chemistry, it has to do with how much it acts like a metal. Right? How much it acts like a metal. So the things that are really, really important for organic chemistry, these top two things. This is super important, super important, super important. These two are linked, but they're not the same thing. This is how much it likes electrons, and this is how much it becomes more negative. Okay, how are we doing with this so far? All right. So the trend for those top three things is this direction. Metallic character tends to be a bit more like this. Metallic character increases the more we go this way. But that makes sense. Most of our metals are on this side, right? So we would be moving away from the non-metals. MC chemistry. Would be like a new degenerate. All right, atomic radius. Atomic radius is this direction. Down and to the left. So over here are our massive atoms. Big. We had, so we got to kind of think about that too. Atomic radius is kind of linked to these other things. So the majority of an atom, we're like, well, it's mostly empty space because that's all the electrons. There's space between those electrons. But if you've got a lot of electrons and you don't care for electrons so much, they're going to spread out more, right? Ones over here are going to have a smaller atomic radius because they're going to be pulling those electrons more towards it. Does that make sense? Over here, they're going to be spread out more because those atoms don't have such an affinity for those electrons. Another thing to consider when we're talking about the behaviors of different groups. If something really likes electrons, it's going to be really hard to take an electron away from it. So that ionization energy, fluorine, good luck taking electrons away from fluorine. It's going to require so much energy, it's not worth it. But you move over to this side, like this group, it will throw electrons at you. It's just no major energy at all required to take an electron from here. So part of what we need to understand for organic chemistry, stuff over here, not likely to give up electrons, it's going to take them. Stuff over here, going to throw electrons at you, doesn't care about it so much. So in the terms of organic chemistry, things that we've got to keep in mind, elements that love electrons, that's going to be important. Elements that take electrons, that's going to be important. Hey, Dr. Domus, how you doing? Awesome. You want to come in and learn some chemistry?
Yeah,
You sure can. Come on in.
I just learned how to hand wash.
Ah, yeah, that's important.
Today.
So we've got elements that love electrons. We got elements that take electrons. So when you're going through these periodic trends, keep in mind that the ones on this side This is going to be our super electronegative atoms. So they're also going to be the ones that are going to become more negative. That will hold a negative charge. Okay. So what's the pattern here that you see between these? What do you guys see the pattern here? What's an underlying theme between the three of these? Electrons. What loves electrons? What doesn't love electrons? So all of these things, essentially, pretty much all of organic chemistry is where are the electrons going? Where are those electrons going? So think about it. Are electrons stuck in a particular bond and they move around? Yeah, they can. Electrons can move around, they can push other electrons out of the way. All we're looking at with organic chemistry is where are the electrons going in regard to the patterns with carbon, hydrogen, oxygen, and nitrogen. So we're looking at how these particular elements interact with each other, where the electrons would go in these cases when they're all paired up with one another, and what's likely to happen. What's likely to happen? Okay, so let's apply some of this. So let me ask you, which one is more electronegative, do you think? Carbon or oxygen? Oxygen, why?
It's
more over to the right. Well, we can also check those numbers. Carbon has an electronegativity of 2.55. Let's see if you're right. Oxygen is 3.44. Yeah. So that's a big difference. So oxygen is going to want to pull on electrons more so away from carbon. So over here, when we're dealing with covalent bonds, where those electrons are shared, y'all talked about it before with the polar, remember polar and non-polar? Polar bonds have an uneven sharing of electrons. So on those little summary sheets that you've got, so if I have, for instance, carbon dioxide, we drew out those Lewis structures last time. And I've got a pair here, 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 here. Okay, here's a question for you. Where are the electrons going? I clearly have electrons in these bonds. Is there uneven sharing happening here? No, yeah. This is a tricky one, isn't it? Is this one more electronegative than this one? Yeah, so oxygen is going to be pulling on these electrons this way, right? So I'm going to just draw a little symbol that way. What about here? Is it going to be doing the same on this side? Yeah, you think so. So I've got electrons moving this way. So clearly I have uneven sharing in these bonds. But what about the whole thing? You got a tug of war going on. This whole thing is non-polar because these two are canceling each other out. So the bonds are polar because oxygen's clearly pulling on these electrons. But they have an equal tug of war happening with that carbon. How are y'all doing with that? let's have a look at something. There's another website that I use, and I think you have a link to it in the module. Here we go. These simulations are very, very helpful. Let's look at, I found out recently that you can alphabetize this, which has made my life easier. Let's look at molecule polarity. Here we go. I like this because you can kind of see that uneven distribution of electrons. So let's pull this up. We're going to pull up carbon dioxide. Java doesn't work anymore, but they have something called chirp J, so that helps. All right, so in reference to the shape of these molecules, let's pull up carbon dioxide here. Okay, so I've got my individual bond dipoles. So you kind of see, you can move these around. Isn't that neat? So I've got my electrons moving that way, and I've got my electrons moving this way. I can also show the electrostatic potential and the electron density. This all kind of looks like the same color, doesn't it? Almost like they're evenly kind of spread out, even though these bonds are polar. Well, let's see if there's a positive and a negative side. So if you had a magnet that had two negative sides and the middle positive, would that work so great? Would that be a good magnet, you think? That'd be like a terrible magnet, I would think. So a polar molecule has to have a distinct positive and a distinct negative side. So I'm going to add another little thing here. Polar molecules must have a distinct, what's another word you could use there? Obvious, that's another one. Must have an obvious, distinct positive and negative side. That means, oh wait, let me spell better. There's no spell check on the board. All right, distinct positive side and a distinct negative side. This doesn't work. You can't have like two positives and a negative in the middle. You can't have two negatives. You can't have anything like that. The only thing that works is this on one side and this on one side. These are terrible magnets. You have to have distinct poles for that polar bond. Well, let's look at another one. I'll see you later. Okay, water. Let's look at water. What do you think here? You think what?
Yeah, it's non-polar.
You think water is nonpolar? Let's see. What do you think?
You have
Let me show the atom electronegativities. Is that a big difference? Well, if carbon's 2.5 and 3.5, that's a big difference. That's 2.1 and 3.5. So I'm going to give you a pro tip. For atom electronegativities, if it is 0.4 to 1.9 difference in electronegativity, polar. What do you think? What do you think? So the difference between hydrogen and oxygen, how does that relate, you think? Polar or non-polar, what do you think? I think it's non-polar, Miss Williams, or I think it's polar, Miss Williams. Or I could do like maybe a guy voice. I think it's polar, Miss Williams. I think it's non-polar. Where are my non-polar people at? You think it's non-polar? What about my polar people? You wanna raise your hands? Okay, yeah, it's polar. Thank you for raising your hand. So yes, I can see that's the overall molecule. This is going this way, moving towards the oxygen. These electrons are moving here. This is going this way, right? So I can see, I would expect electrons to be more on this side than on this side. Let me see if that's right. Look at that. The electrons are moving up towards the top here. They're less so down here. So would this have a distinct positive side and a distinct negative side, do you think? I'm seeing some nods. So let's see. Look at that. Distinct negative side, distinct positive side. So is the overall molecule polar? Yeah. Y'all got that. So as we're moving through this, again, the theme, where do the electrons go? Where are they going? They're moving this way, moving this way. So since they're side by side like that, I mean, that one has 2 bonds. This one has 2 bonds. But why isn't this polar? That one's polar, but this one isn't. What do you think? What do you think? What are the main differences between those 2 molecules? Come on, tell me. I see you nodding your head back there. What you think?
Where the oxygen goes, this has the electrons on the inside.
Okay.
And on the top.
All right. So where the oxygen is, so maybe the shape of the molecule plays a role. If for whatever reason this, and this isn't correct at all, but if it looked like this, then we would have a positive side and a negative side, wouldn't we? But that doesn't comply with the laws of physics. These electrons are going to push as far away from each other as they can. So that isn't the case. So we have a whole lot of electrons here and a whole lot of electrons here. They're going to push each other out as far as they can go. So a caveat for this, shape of molecule. Can you tell I replaced it with green? I kind of like it. It's like you see the transition from blue to green. Shape of molecule plays a role. Plays a role in polarity. Right? The shape of the molecule plays a role in polarity. So if it's straight across, It's non-polar. It's bent shape. It's polar in that case. How are y'all doing with this? It's so much. It is a lot. Have y'all met Miss Steele? Y'all want to meet her real fast?
Did you bring her in the first time?
Did I? Okay, all right, maybe I did. She can help with the general chemistry stuff. Okay, so let's take a look at our objectives and see where we're at with this. With Unit 1, are you guys having any concerns with some of this? No? You're gonna have to give me some feedback. If I gotta walk around and look at your notes, come on, give me some feedback here. Which part of these objectives do you feel like you're struggling with that we've covered so far? Y'all doing all right with Lewis structures now that we've kind of gone back through that a little bit? Okay. What about the octet rule? The ones in row 3, sulfur and phosphorus. They're the ones that can go to 10 and 12 because they're weird. You pull from that d orbital. That's the ones that break that rule. Covalent versus ionic. We got that down. Non-metal, non-metal, covalent metal, non-metal, ionic. All right. Is electronegativity making more sense now? Something loves electrons, it's going to pull it more towards itself. Okay. Alrighty. Let's have a look at resonance forms. We've talked about polar molecules, movement of electrons. Honestly, this needs to be the first question you ask every time you look at a reaction. Just try to keep that in the back of your mind. Where are the electrons going, right? Where are they going? All right, I want to have a look at that summary sheet. What do y'all think about those summary sheets? Are they helpful? Are they overwhelming? You know, you can love them or hate them, it's fine. Maybe you can rewrite them with pictures, you know? All right, so the things that are really, really important to take note from these summary sheets. Okay, hybridization, shapes of molecules, we're getting into dipole moments. So this polar stuff, you can also label polar, non-polar. Another word we might see is dipole, right? Another word we might see is dipole. Formal charge of an atom. The thing that I want you guys to think about the most when it comes to formal charges. Elements, let me see, let's write that down over here. Elements with the higher electronegativity, that's what EN means, electronegativity. Elements with a higher electronegativity will take the negative charge. So if you have to put a negative charge on something, it's going to be on the element with the higher electronegativity. So when you're building a molecule, let me show you an example. Polyatomic ions are really good examples for that. Alrighty. Let me show you an example. Okay, here's one. Now we're kind of delving into that open image nitrite. This is a polyatomic ion. What does that mean, polyatomic ion? Y'all remember? Poly means what? You got mono, di, bi, poly. What's poly? Many. All right, so poly means many. So a many atom ion. You got a lot of atoms stuck together, form an ion. Most of the time they're going to be non-metals. So look, what's going on with this one? What do y'all see the difference between this one versus this one? What do you see? It's like point out the differences. It's kind of how you read it. It's like a mirror, right? Kinda. So we got double bond switched on the oxygen, same with the charge. This is called a resonance form. So when I think of resonance, I think of music, or if something resonates with me. It's like I get that, you know, I'm picking it up. Resonance in this case has to do with movement of electrons. So electrons are constantly moving. And here, they can shift back and forth between these two bonds. So when you draw a Lewis structure of certain polyatomic ions, you can draw it this way, but you can also draw it this way. This arrow means it goes back and forth between the two. So when we're talking about resonance structures, black marker is over. Okay. When we talk about resonance structures, I'm going to make a note. Resonance structures are the different forms of a compound that shows the movement of electrons. Right? So that movement of electrons is happening between bonds and atoms. Now here's a question for you. Why is that negative charge on that oxygen and not that nitrogen? What y'all think? That's exactly right. Oxygen is more electronegative. It likes electrons more than nitrogen does. Has a higher electron affinity. So this oxygen is going to hold that charge and not the nitrogen. How do I know that? Where is it at on the periodic table? It's right here. So oxygen, when it's hanging around the nitrogen, it's going to take and hold on to that charge. Both of these forms are valid forms of this molecule. So electrons can move between atoms. And that's what resonance structures are. Let's look at another example. Here's NO3. Check this out. Open image and new tab. So my search term for this was resonance structures, polyatomic ions. So if you're wanting to look at more examples of this, you can look for images. I like images better than words. How do y'all feel about that? Do you like images better than words? Your eyes glaze over when you see lots of words? I mean, I do. So it was like, here, read this 30 series of tweets. No, where's the TLDR version? I'll sum this up pretty quickly, right? I like pictures better than words in that case. So what's going on between these? Last one was nitrite. This is nitrate. How is this one different from this one? What are the differences here? What's the first thing that jumps out at you? There's 3 oxygens. This one had 2, right? We also have 2 resonance structures. This one has how many? 3. So if I were to assign a charge somewhere, here they've written it to where it's in the brackets and the charge is on the outside. Which atom would actually hold that charge? First of all, which element do you think? Nitrogen or oxygen? Oxygen would, because it likes electrons more, right? So if I had to assign a charge on one of these, it would, let's see, we got 2, 4, 6, say 2, 4, 6. I would assign it on one of these single bonded oxygens. Just like right there. So it's really important to pay attention to resonance structure. So when we're looking at, where did it go? Here it is. When we're looking at these, when we get our resonance structures here, or were they somewhere else? Were they the last page? Here we go. Hybridization, curved arrows. Okay. All right, it doesn't say it on there. So it's really, really important to recognize where the electrons are moving to. So things to pay attention to on this sheet. Hybridization, we're going to get to that next class. What is a pi bond? And review a little bit on geometry. I think I have some helpful images here for molecular geometry. If you look under helpful images, I've got some images here that'll help out with that. Next class, we're gonna knock this out of the park. We got hybridization and the shapes of molecules. If you're like, I need a good review on shapes of molecules, this little PHET website, they've got a great simulation, and it's called Shapes of Molecules, or Molecule Shapes. You can go and have a look. It's 3-dimension, and test your knowledge and kind of get a refresher on your molecular shapes. And that's that PHET website. I have a link to it in the resources in Canvas. Okay. Well, that's all I got for you guys. Let me turn this off so we can do this next time.